This is Junkawan with Nightcap. This is a new series. Tonight's interpretation is brought to you by the Sustainable Minerals Institute in Queensland. They have just provided a dataset. Is the Thalanga VMS deposit from Queensland. This has been a fairly famous area for studies of VMS deposits, and of course all of these deposits are considered to be syngenetic. Of course, I'm going to ignore all of that and just do the interpretation straight from the raw data. So that's what I'm going to do. But you can pick up the data from the LinkedIn post that they put up. And yeah, it's a fantastic data set, so have a look. I can provide you with the desurveyed grade data of copper, lead and zinc that I'm using on screen now. So let's get started with the copper data. So I'm looking at a plan view here. So the overall trend of this mineralized zone is trending east-west. If I look towards the north, you can see that the plunge of these deposits differ depending on where you are. So on this side, everything is plunging towards the west. On this side, everything is plunging towards the east. So how can we interpret this? Now, first of all, one way you could interpret it is that there is a series of folds that are dipping in opposing directions. So over here on the western side, the folds are dipping towards the west. And on the eastern side, the folds are plunging towards the east. You'll notice that the copper is high grade up the top and it dissipates downwards. And if we look at the lead and zinc, it's kind of the opposite, which is kind of interesting. I don't understand it. But I can work out the gradient from this, and I have a little switch here. That's the gradient for copper. So that's increasing in that direction here, upwards. And if I switch over to lead and zinc are both facing downwards. So they increase, the actual gradients are quite different. Now, one thing about characteristic of VMS deposits that I've seen all over the place, and it seems to be the same theme over and over again, is a lot of them are folded, and if you look for the folds, you'll find them, and often they are running along, or the grades are running along parallel to the fold axes. So this will be a candidate for me. But then there's a break. There's a straight break here that cuts across the grain. If that is the fold axis, then yeah, it's truncated. So let's see if that hypothesis is true. So I'm going to look over here, and you can see over on this side, if you look down plunge, you can see that this sort of like a fold-like feature. So I expect that to be a fold. That sounds like a good possibility. And if I go over here, I'm looking down plunge, and here there's another candidate possibly for a fold here. So I suspect that what this thing is parallel to a major foliation, and there are interfoliar folds within it. Now, all this is speculation, of course. I mean, you have to check it out with drilling data. But I've seen some of the photographs of this drilling, and it's highly strained. So it's very consistent with what you see in the photographs. So here's another clue here, possibly that there is another fold running through here. So there's an earlier fold. Now, if you look at it here, you'll look at the copper appears to do this. Yeah, so there's another fold axis running like so. Okay. So this appears to be parallel to this zone here. So it could be the same fold, but the fold axis is at a different orientation, obviously, from the other one, which is interfolial. It's parallel to the fold, the foliation there. So there could be two sets of folds, or this could be associated with this refolding event here. We don't exactly know. We just have to take a guess at it, but I think folding is a likely candidate. So how do we interpret this side? Now, it's interesting that this trend here is pretty similar to what you see here. So I suspect that what you have over here is probably the same fold that is just simply just a bit steeper over here. So if I go over here, can I see some clues? Possibly here. That could be a possible isoclinal fold nose right here. So this is the type of thing that I look for all the time, is that when you see high grades, then zoom in on it and to see if you can actually sort of spot anything. This is lead. Lead. It's possible that that could be an isoclinal fold, but I need confirmation. Okay, so most likely there is an earlier fold that is plunging towards the west, and that is consistent with the fold structure over here that we could find. But what about these trends that are cutting across it? Most likely there's a faults that cross-cut the fold grain, and this is quite a common feature of mineral deposits, and it doesn't have to be VMS, volcanic hosted sulfide deposits. It can be gold, it can be nickel, it can be all types of deposits, copper. It makes no difference what commodity you're dealing with. These are quite common features, and I call these Perkins discontinuities because Bill Perkins in the Mount Isa deposit, he was able to identify these at the hand sample, but you can actually see these things in gold deposits all over the place repeatedly, and they are late faults that cross-cut folds. Now, some people believe that these straight faults are faults that survive folding, but that's just simply not possible. So I would say that this is a late fault cutting across, and this is probably a series of faults that are cutting across the same way. It's the same orientation. I know that this has been interpreted in a different way, and this is let's see, this is a thesis by a PhD student from UTAS, and this is the interpretation that was presented, and this is actually in the handout from the Sustainable Minerals Institute, and she felt that these are faults, that is, these things are faults that slid down like this, and they have to be put back like this in order to make the original configuration. But is that possible? Now, if you look at the zinc, that is quite possible because you can see high grade here and high grades here. So if you slide this up and match this with this, you could argue that they match up. But if you look at the copper, it's different. Over here, it's quite low grade, and this is high grade. So if you slide that up here, low grade will be adjacent to high grade. So I don't think that's possible. You can't sort of slide that up. And on top of that, there's a possibility that this is a fold nose. and we've seen the repeated likely fold limbs over here. You can actually sort of see it. So I think this is more like a fold hinge that is a high grade. So that's not consistent with the fact that this could be a fault, but most likely this is a fracture that dammed up mineralization on one side. Okay, I can look at some trends, structural trends obtained from the grade, and I do this through a process called LVA. I've given a talk about this if you're interested in hearing about it. So copper foliation looks like this, and you can clearly see that the foliation follows along the grade, and I can color this according to copper. Yeah, so you can see the step in that area, and the folding here, and you can see that what did I have in the grade? Grade is quite scattered. It can be going all over the place, but you know, this is quite a linear zone, so I can plot that, and the lineation is scattered, of course. Now I can go and just select this area on one side, and it'll be clearer. So that plunge is towards 59 to 300. So if I press that, I'm looking towards 60 to 301. So approximately the same. And yeah, the lineation, of course, is plunging in that direction. How about the zinc and copper would be the same. Zinc and copper would be the same. So that's the lead, not zinc and copper, but lead and zinc are the same. That's the lead, and that's the zinc. Same plunge. And over on this side, we have a different set that is plunging the opposite direction. That's the copper. Yeah, it's very planar. It's not linear like the other example. It's very planar. That's interesting. Yeah, it's very planar compared to the other side, which is interesting, because when we looked at the other side, over on this side, the linear trend was actually stronger. See that there's a linear cluster over here, which supports the view that the fold axes are actually going in that direction, plunging in that direction. So this is a fairly planar zone of continuity. So this is kind of important. I mean, you can do this LVA and find out this is, largely planar. Whereas this is a triaxial sort of linear planar system over on this side. So the hypothesis that the fold axes are plunging towards the west is most likely the case if I were to put my bet on which side the folds are plunging. So in summary, I see at least two sets of folds here. One set that is parallel to here, plunging towards the west. Of course, this is all speculation. It needs to be tested and need to look at the core and do some field work, obviously. And there's this broad fold, open fold, plotting the foliation, grade foliation, and this open fold. You can plot that using this, and the plunge is about 74 to 137. In this direction here, 75 to 138. So that direction is the second fold. It could be the third fold. So that actually gives you a summary of what's going on. Okay, let's compare this pattern to what we find in the property of sunshine. And you can see immediately that what sunshine has is very similar to what the patterns that you see here. They say that it's all open in this direction, according to this. Now, maybe this is the direction of their fold axis. I don't know. See that this feeder issue, I think this is completely fiction. Yeah, this is fiction. Okay, so they considered these to be feeders orthogonal to the main trend. Now, I have no doubt that the main trend that they have is highly strained, like what we see in this deposit we've been examining. If you look through their drill core, they'll probably show you nicely foliated rock. Not entirely clear here. It says it's foliated. Not entirely clear. It's not pervasive. It doesn't look pervasively foliated. I haven't looked at the details, but there's a simple reason why you can't preserve orthogonality when you have highly sheared rock. This is like, you just imagine if this is the feeder to a bedding surface, which horizontal, okay? This is undeformed state. But as soon as you start to actually squeeze it and deform it, you cannot retain that right angle relationship. You just can't. So there are academics, well, it's not just, it's not just these companies. These companies are depending on academics to actually analyze VMS deposits. And the academics are saying that they see this type of geometry in nature. So that's why they draw these feeders. Now, that can't be physically possible. Like, it's just impossible. You can't do that. You can't end up with these things being right angles. I mean, if anyone can demonstrate that to me, I'd love to see it, but it's just pure fiction when you're dealing with strained rock. So that's my brief analysis. I only really looked at this for an hour, and I only just downloaded the data today, so I haven't really had much time to look at it. But there's a lot that you can get from just looking at grade data. And note that I didn't sort of interpolate anything using Leapfrog. I mean, you don't need to. I've come to the conclusion after working with mineral deposits for, nearly 25 years now. I just use the raw data, and I can analyze the raw data with my LVA technique that no other software is able to do. And I can structurally analyze mineral deposits like this, work out their plunge and likely structural information at the deposit scale. So, all this predictions that I made are testable. They're falsifiable hypotheses that you can actually sort of go there and look at the core, or go in the field and map the actual rocks. So they're very useful information. Now, for those who want to learn this particular technique that I use, I have a workshop that I'm running for companies. If you're interested, I'll leave some information in the article that accompanies this video. Thank you very much.